All right, I'm back. I'm actually going to be talking about page 269 in this video, but I wanted to point out that page 266, so these are all review topics. I have actual videos, not that this isn't an actual video, but probably not going to post these publicly on my YouTube channel. So I have actual videos on my actual YouTube channel that cover the material here, and we don't cover these in class. So what I think I'm going to do this year is I will do the problems. I will export the PDF so that you can see the solutions that I got and you can compare and make sure that you're getting it right, because you know, when and where can you ask questions? Like, who knows? So I'll do that. So I'm going to do these problems. I'm going to do these problems. And I'm going to do these problems. And I'll post the PDF. It'll be in the same place that you found this. And then I'm going to get going on this. So this is where we usually pick up again in class. We never do those pages in class anymore, so not really a loss. You're not missing anything. Let's talk about this. So this is page 269. It's about factoring out radicals, factoring out of radicals, not factoring out radicals. And this is a really big important idea, especially because we want to talk about limits. And when you go to infinity and negative infinity, when you're taking square roots of things, it's like, it just gets weird. So we need to know a couple of things. So the first thing that we need to know is we need to make sure that we definitively remember this fact, that the square root of x squared is, lagging here. I think it may be caught up. The square root of x squared is the absolute value of x. Now, it's not really relevant at this exact moment, but we can also further say that it's this piecewise function. It's the opposite of x when x is less than 0, and x when x is greater than or equal to 0. So it doesn't matter where you put the equality. You could say it's the opposite of x when x is less than or equal to 0. You only put the equality once. Yeah, I mean, I guess that's all I really have to say about that. So let's see what we can do. So there's some weirdness, right? So the square root of x to the fourth is, so remember, square root is like to the 1/2 power. So it's like x to the fourth to the 1/2 would be technically the absolute value of x squared. But then x squared is always positive, so you don't really need the absolute value. Whereas, so this is x squared is greater than or equal to 0. Therefore, the, what am I doing? Let me move this over and then say, therefore, the absolute value of x squared is x squared, because you can never get a negative out of it. On the other hand, the square root of x to the 6th, so it's x to the 6th to the 1/2 x cubed. Well, x to the 6 over 2 is x to the 3, which is x cubed. Sometimes that's positive, sometimes that's a negative, so we do need the absolute value. So here, since x cubed is, what is the symbol for not greater than or equal to 0? I'm not like this might be made up. It is not greater than or equal to 0. I don't know. I think that should be a symbol. It's not greater than or equal to 0. Therefore, you need the absolute values. So the safest thing to do, I guess, is to always leave the absolute values, but be aware that some people who really understand this stuff will drop the absolute values when they can. You don't really need to, but you probably should if you can. So what are we going to do with this? Factor the highest logical power of x out of each of the following using the idea above. So these are they feel like weird problems. What we're going to do is ultimately we're going to take the limit as we go to infinity or negative infinity, so it'll be relevant. But for now, this is just a skill that you definitely need that maybe you're not so great at right now. So let's see if we can do it. So the highest power I see stop. The highest power that I see inside the radical here is x squared. So I'm going to do this. X squared, take x squared out of everything. So when you're not sure what that means, factoring something out is equivalent sort of to dividing by it. So x squared over x squared is 1. 3x over x squared is 3 over x. And then minus 5 divided by x squared is just minus 5 over x squared. So I found the thing I just wrote in parentheses by dividing the original thing by x squared. then I leave the x squared there, because if I distribute it, I get back to the original, which is like the entire point. And then I see the square root of x squared. So property of radicals, square root of a times b is equal to the square root of a times the square root of b, provided that neither a or b is negative, but we don't worry about that part right now. So this would be the square root of x squared, the square root of 1 plus 3 over x minus 5 over x squared, which is the absolute value of x, square root of 1 plus. I think it was in these videos that I talked about how I was going to try to start doing radicals differently, right? I was going to like make the little like check mark, do the whole radicand, and then do the like line over it. Obviously that didn't take. But anyway, this is our answer. That's as good as it's going to get. So we do the same thing here. And, you know, once you get what's going on, you skip this step for sure. And then you probably also skip the next step that I'm going to show, which would be the square root of x squared. I would definitely skip that step, but I know what I'm doing. So you kind of have to like make that choice for yourself. Like, do you know what you're doing? If you do, you can skip steps, but it's a risk, because when it doesn't go well, teachers are not super sympathetic to the fact that you took the risk when you could have avoided the problem by not taking that risk. So, you know, you're playing with fire. All right, let's see here. Highest power that I see is x to the 4th. So I'm going to try to take that out. Let's do the radical thing. There. And take out x to the 4th, which will leave me with 1 plus 3x squared over x to the 4th, 3x squared minus 9 over x to the 4th, and then close it. It works well. Like if I could convince myself to do it. All right, square root of x to the 4th is technically, so we should start with the absolute value of x squared, and then the square root of 1 plus 3 over x minus, 3 over x squared, 9 over x to the 4th. And then I'm thinking the absolute value of x squared is never negative, so I'm going to drop the absolute value. But you could leave it, like it's not the end of the world, it's just unnecessary. It's like putting a random extra set of parentheses around something. Like you don't need it, but it doesn't hurt. And if you needed it and you got rid of it, it would hurt. So I don't know. You gotta decide for yourself what you're gonna do there. Here, let's see. So this one, there's really nothing much to do. So x to the 14th to the 1/2 is x to the 7th, but absolute value, which I would definitely, too long. I would definitely leave that. But you could, so like leave this, leave that. But let me change color here and do some weird random garbage. This is the same as the absolute value of x to the 6th times x. And then the absolute value of x to the 6th is just x to the 6th. We could do that if you like needed to. I can't think of a scenario where you need to do that. But it's true. So like you could do it. I don't know. All right. Do I want to do these here? All right, I'm going to do a couple of these here. So as I defined above, accidentally, without looking at the notes ahead, which is one of my personal flaws when I'm doing this. I never look ahead in the notes, so I'm never really sure what's coming up. The absolute value of x is actually defined as a piecewise function. It is a really nice shorthand for a piecewise function. And because it's a shorthand for a piecewise function, the absolute value of x has some weird properties we'll find in calculus that other functions that are like easy to write don't necessarily have. But it's all because it's hiding a piecewise function. So the absolute value of x, I mean, just think about it. Like some people are confused by this definition, but if we had to do like the absolute value of -3, that would be the opposite of -3, right? It'd be 3. Or the absolute value of -10 is going to be the opposite of -10, which is 10. So the absolute value of x when x is less than 0 is the opposite of whatever x is, which is where this part comes from. The positive part just makes sense. It's going to catch up. There we go. A more general form of this is you can actually just have like u, the absolute value of u. This feels the same, right? Because I just like changed the letter that I'm using. The absolute value of u is equal to u when u is greater than or equal to 0. The opposite of u when u is less than 0. It's hard to talk about this because it sounds like you're just murdering grammar. But we're then able to make u be like any random f of x. And so that's where it gets more interesting. So let's see if we can do that. I'm going to try to take these absolute values and rewrite them as piecewise functions. We did something like this in like notes 13 around the rational functions, like around it. It's like a random thing. So you may or may not remember it, but if you go back to notes 13, you'll find some stuff about it. All right, rewrite each of the following as a piecewise function. Here's how I do this. All right, so if I need to figure out like what makes this equal 0, so maybe I should not just do that. Gives me x equals 3. All right, and then what I'm going to do is I'm going to look at what happens to x minus 3. Here's 3. All right, when x is less than 3, so like 0, for example, will give me a negative. I like to put a bunch of those. I usually put 3 if I can, for reasons that will soon be clear to you because we're getting really close to dealing with this. But put a couple of them. Don't just put one. If x is like 50, this is definitely positive. Okay, so why did I do that? I did that because I'm going to use this information. The absolute value of u is whatever u is when u is greater than or equal to 0, and it's the opposite of u whenever u is less than 0. So how does that apply? Well, that's u, right? And I just figured out when u is less than 0 and when u is greater than 0. So let's write this down. So this will be, it's just equal to u, x minus 3, when u is greater than 0. U is greater than 0 when x is greater than 3. So I'm going to say, I'm going to do greater than or equal to, because I feel like I like to put it with like u. You know, u is x minus 3. I like to put the equal part there if I can. And then it's going to be the opposite of u, so the opposite of x minus 3, which you could definitely write as 3 minus x, but like it doesn't really benefit you. So like, why do that? But you know, I'm not going to be able to talk all you out of not doing that in my experience. Like I know that going in. So let's see. So in practice, you don't need to do as much work, but you can. So I mean, here we would get x is 4/3. Then you can make a number line or a sign chart, whichever you prefer to call it. I would prefer if I always called it a sign chart, but like I learned it as a number line, and so now I always just think of it as a number line. It is a number line. I mean, it doesn't hurt to say that. So this will be for 3x minus 4. If x is 0, I get a negative. 0 is a good thing to, negative a billion is a good thing to test. Positive a billion, like go really extreme. Plus, because there's definitely a sign change there. All right, so we're going to get 3x minus 4 when x is greater than or equal to 4/3. And I put the equal to on that one because u is equal to 3x minus 4. That's like how I make that choice. It doesn't matter. You can put it on either branch because you get the same value from both branches at 4/3. So like, who cares? But, and then the opposite of 3x minus 4 when x is less than 4/3. There you go. That's it as a piecewise function. I'm gonna do this one, then I'm gonna cut the video and come back and do the rest of them. So here we go. First, let's factor this. Well, maybe we can factor this. Okay, so I like to go with x and x, and then I just think like what multiplies +6 and adds up to -7. So -1, -6, close my absolute value. All right, I'm gonna do the same thing here, except it's a little more complicated. So I'm gonna put 1 and 6 because they're the zeros of this and this. Different color would be better because they're the zeros of this and this. And I'm going to test regions, right? So I'm not testing with the absolute value. I'm just testing the absolute, no, without the absolute value. I literally just said that. I'm just testing x minus 1 times x minus 6. Negative a billion will give me, so negative a billion will give me a negative here and a negative here. Negative times negative is positive, so it's always going to be positive here. Another way to think of it is that this is a quadratic that opens up. And a quadratic that opens up will go positive y values, negative y values, positive y values, or whatever. All right, 5 would give me a plus, but also a minus, so negative. And then a billion definitely gives me positive, positive. Get this. All right, so you can write this 2 different ways. One option is with 3 branches, which is what I would do. So but I always go back to the unfactored form because I think it just looks a little better. So it's going to be x squared minus 7x plus 6 when x is less than or equal to 1. It's going to be the opposite of that. So notice I'm not distributing because, like, what do you gain by doing that? So the opposite when you're between 1 and 6, and then it's back to the original when x is greater than or equal to 6. And I could have put the equal one, or equal to, on either branch. It wouldn't have made a difference. So this is option 1. I think that this is the best thing to do. You also could do, so I'm doing a different color, or you could do x squared minus 7x plus 6 when x is less than or equal to 1, or x is greater than or equal to 6, and then also the opposite of parentheses, opposite of x squared minus 7x plus 6 when x is between 1 and 6. Like, they're both right. And you can do either. I prefer the one with 3 branches because it makes it like very visually clear what's happening. And I think clarity is always really important when you're like choosing your notations and things like that. But I'm going to stop here and come back, finish this page in the next video, and I will see you then.